Hello, I'm David. I'm the coordinator of the Maths Learning Centre at Uni of Adelaide. It is semester 1, 2023, and this is a revision seminar for multivariable and complex calculus. And we will get started in just a second. So as usual, those who are here, those who are here live, one of your jobs is to tell me if I've missed something that has been said in the chat. So please let me know. And also, it is everyone's job to ask me questions. It is okay to interrupt me. If you interrupt me without letting me get a few, 2 or 3 words out at a time, I will start to get annoyed, but overall I will not be annoyed because I like people asking questions. Yeah, this is your revision seminar, not mine, so you're the one who has to do the exam, so please ask me questions if you feel the need at any time. Okay. I'm going to talk about optimization in the context of multivariable calculus, and it might just be easier to run through an example and maybe pull it back later, but I will also, I think before that I just want to talk a bit about my thoughts on it, and feel free to add anything as you go. Okay. So, there are 2 different kinds of optimization as far as I can see in this course, and one of them is unconstrained and the other one is constrained. Is that the words that they use for it? Does that sound right? Global extremer. Yep, okay. So there's a theorem that goes that function f that sends a domain to R, where the domain is inside Rn. Just give me a sec. Is closed and bounded so your function has to have its global extrema, which means maximums and minimums, occur at a local extrema in the interior or on the boundary. That's the theorem. And both of those things, of a local extremum in the interior of the shape or an extremum on the boundary, have their own ways of doing things. And so the process, if you just start with a question that asks about one of those, can be quite long because it has 2 separate parts. Okay, so a local extremum in the interior of some zone has to happen at the place where the gradient is 0, where the first derivatives are all 0 simultaneously, and you can tell based on the Hessian of second derivatives whether it's a maximum or a minimum or something else. That's the first bit. This is what I've got in my head. So therefore, just a second. to find the maximum minimum, you have to, 1, find all the local extrema inside, and 2, find the maximum minimums on the edge. Okay, cool. And 1 requires you to find the places where the gradient of f is 0. Is that how they write? That's how they write this? All the first derivatives have to be 0. And only choose the ones that are actually inside the region. And number 2 is with Lagrange multipliers. Cool. And so I need to talk about both of those, or at least show them up in an example in order to make that work. How are we feeling about that summary of what has to happen in order to do it? Or F, underline the nabla. Cool. But F itself produces a number as the answer, so it's not underlined. Sure. Why not? Well, that makes sense. In one-dimensional calculus, if the derivative is undefined, that's also a place where the maximums or minimums can occur, like with the absolute value function, it's got that kink at the bottom. Thank you. So you're asking about the Hessian. Technically, you don't need to use the Hessian in this process because we're going to just find all of the critical points and sub them all in, and whether the Hessian is whatever it is, it doesn't matter because the maximum will be whichever of them gives you the highest value. So, but the Hessian is related to this. It's related to this. The Hessian will allow you to decide whether it's a local maximum or a local minimum. So I will just add that there. But that's what it does, but technically you don't need it in this process. All right. So it might be easier just to run through an example, really. And there's one from a tute, so I might do that. So we've got f of xy is equal to x squared plus y squared minus x minus y. Find the global extrema on the region where x squared plus y squared is less than or equal to 1. So the very first step of this is probably to draw maybe not a picture of this, but at least a picture of this, just to have a feel for what's going on. And x squared plus y squared is equal to 1 would be a circle of radius 1. And x squared plus y squared is less than or equal to 1 is everything inside the circle of radius 1. Okay, So the theorem says that if you have a region that is closed and bounded, and that is our region, is definitely bounded because it has an end, it doesn't go forever, and it is definitely closed because it includes its edge, then the maximums and minimums will happen either at a critical point inside the interior or on the edge. And we're going to have to deal with both of them. So first we need to, first we have to find the critical points. They call them critical points, don't they? Yeah. I should put that here. Critical points. Okay. So find the critical points where the gradient of f is the 0 vector, which in our case will have two coordinates because there's two variables, so it'll be df1 dx and df1 dy, or f sub x and f sub y. So let's see. So the derivative with respect to x is 2x there, and then y doesn't involve an x, so that'll go away, and then a -1, and then that'll go away. And f sub y would be 2y minus 1. Okay. Okay, and so we need both of those to be 0 at the same time. I'm going to give them numbers. So from number 1 we get that 2x is equal to 1, so x is a half. And for number 2 we get 2y equals 1, so y is a half. And that is here, which I'm pretty sure is inside the circle, but I should check. Have I done that right? Okay. So I just should check if that's inside the circle, because if it's outside the circle, I don't care. So half to half. I think it's inside the region, since a half squared plus a half squared is a quarter plus a quarter, which is a half, which is less than 1. So yes, that's okay. It is definitely inside the circle. Cool. So that is going to be one of our places where the maximum or minimum could occur. Okay. Sweet. And if I knew what the function value was at that point, then I would be able to figure it out. But I'll come back to that. So we have one critical point so far. So cool. And if there was more than one, which I should do an example of, if there was more than one, then I would have a list of several of them, and I would have to find which of them were inside the circle. Okay, cool. So that's great. So we've got number 1, we found the places where the gradient is 0, and we choose the ones that are inside the region. Cool, and now we're going to do Lagrange multipliers for optimization along the boundary. So the idea in my head goes, I can imagine this as a surface, and whether I imagine it a surface or not, every point in space has a value for this, and as I track around the circle, that value will go up and down. And so I can imagine going around the circle and the value going up and down and up and down and up and down, and some of them will be tops and some of them will be bottoms, and I should be able to figure out what those extrema are. And I'm going to use Lagrange multipliers to do it. Now, every lecturer does this slightly differently, so I just want to check what your lecturer does. minuses. Okay. So Lagrange multipliers is extremely clever. There's still some aspects of it that I don't really understand, but I do understand. I do know how to do it. So the idea is that you're going to create a new function, which apparently is called the auxiliary function, and your lecturer calls it H. Other people call it L for Lagrange, but I shall use the one that your lecturer uses. I think it's weird to call it H since there's already an H in the derivative when you do the Taylor's theorem, when you do the other thing. That's weird. Do you mind if I call it L? Is that okay? H? Okay. R was the next available letter. Yeah. Okay. So I'm going to make a function of x and y and another variable, which is traditionally called lambda, which is Greek for L, hence Lagrange, right? And so, well, L is English for lambda, I guess, since the lambda was invented first. So you have your original function that you were trying to maximize, and you take off a multiple of the constraint that tells you that you're on the edge. So I'm just going to just point out that the boundary of this is the place where x squared plus y squared is equal to 1. So it's less than or equal to 1 everywhere inside and on the edge of the circle, and the place where it's equal to 1 is the boundary. So it's probably a good idea to write down the equation of the boundary to begin with, and then we have to arrange that constraint in such a way that it's equal to 0. And so we're going to have to write that. It doesn't really matter how you do it. It needs to be equal to 0 for this process to work. And so that constraint that's equal to 0, I'm going to multiply it by the lambda and create this new function, which is a function of x and y and lambda. And the magic trick is that this function has its maximum at the same places where the original function has its maximum, but only considering the places where this is 0. Because this being 0 is the same as the derivative with respect to lambda being 0. It's just, there's a lot of cleverness going on here. And so I have to make the gradient of this function equal to 0. So I'm going to need to do h sub x and h sub y, and officially h sub lambda as well. But this bit will automatically be my constraint, so it'll be okay. Right? That'll be the formula equation for the edge of the circle. So I'm going to get 2x minus 1 like I did before. And in this calculation, that minus lambda counts as a constant, and constants multiplied on are still there after you do the derivative. And the derivative of the inside here with respect to x is 2x. And this will be 2y minus 1 minus lambda of 2y. And this is technically minus x squared plus y squared minus 1, because that is the constant multiplied by the lambda. And all of these have to be 0 at the same time. And my goal is to figure out what the x and y coordinates are that go with this. And I do not particularly care what the lambda is, but it does have a physical meaning, but I can never remember what it is, but it doesn't make any difference to this problem at the moment what the lambda is. So I don't care what lambda is, I just want to arrange so that I can figure out what x and y are. So these two equations will allow me to cancel out the lambda and make one new equation, and then that equation involving x and y has to combine with this one to tell me what x and or y is. If we're very lucky, we can cancel it out to get just an answer for x and then sub that in and get the answer for y. That's normally how it goes. So I'm going to number these. So number 1 was 2x minus 1 minus 2 lambda x is 0. And I feel like putting all the lambdas on the one side. And number 2 is 2y minus 1 minus 2 lambda y. Okay. There are many ways to deal with what happens here. I have to be able to either add them or subtract them or something like that to make them go away, or sub one of them into the other. I prefer not to divide by things because they could be 0. So maybe if I multiply this one by x, I'll get a 2 lambda x and then I can sub this in. Maybe? Or multiply them both by this one by y and this one by x, and then this side will match. That's a good idea. I like that one. No, y. So y times 2x minus 1 is 2 lambda xy, and x times 2y minus 1 is 2 lambda xy as well. And so now since this and this are both equal to lambda xy, that means that they must be equal to each other. Combine them together. Since they're equal to each other, since they're both equal to the same thing, they must be equal to each other. Right? 2xy minus y is 2xy minus x, and they cancel. Oh, look, y equals x. That's cool. Okay. And so this is telling me that the maximums will be in the line y equals x, which is this line here. So it'll be these 2 points here where the maximums and minimums happen. But even if I have a picture of it, you can sub that back into one of these, into the third equation, which I haven't used yet, to figure out what the x and y things are. How are people feeling at this time? So number 3, so we had x squared plus y squared equals 1, because that's officially what number 3 was. It came from x squared plus y squared equals 1 to begin with. So I might as well just put it back there. And x is equal to y equals x. And so I've got x squared plus x squared is 1, so 2x squared is 1, so x squared is 1 on 2, so x is plus or minus 1 on root 2, and therefore y is also plus or minus 1 on root 2, because y is equal to x. So if x is 1 on root 2, y is also root 2 because it's equal to x, and x is minus 1 on root 2, and y is also minus 1 on root 2 because it's equal to x. So now I have 3 points. Half a half, which is a critical point in the interior, and 1 on root 2, 1 on root 2, which is a point on the boundary, and minus 1 on root 2, minus 1 on root 2, which is also a point on the boundary. And the value of f of each of those vectors is a half squared plus a half squared minus a half, which is let's quarter plus a quarter, minus a half, so that's a half, so that's minus a half, and f of 1 on root 2 is 1 on root 2 squared plus 1 on root 2 squared minus 1 on root 2 minus 1 on root 2, which is, well, that's 1 because it's on this boundary anyway, so that's half plus a half, which is 1, so you get 1 minus 2 on root 2, which is 1 minus root 2, which is effectively a negative number, and f of 1 on root minus 1 on root 2 minus 1 on root 2. So that's also 1, and we've got plus 2 on root 2. So my 3 answers are minus half, 1 minus root 2, and 1 plus root 2. So the maximum is definitely this one, is the only positive answer. And the minimum is one of these two, whichever of them is smaller. Root 2 is about 1.4, so 1 minus root 2 is minus 1.4, so it's slightly higher than minus half, so this is the minimum. Yeah, just to be absolutely certain. Yeah, minus 1.4, so this is not as low as this is. So therefore the maximum is at minus 1 on root 2, minus 1 on root 2, and is 1 plus root 2, and the minimum is at a half, and is minus a half. How do you feel? Cool. So that's the whole process. Does that answer what I asked to begin with? Does that answer that question? Was someone in Zoom? Cool. Right, I should just do some waves. I want to do an example where the process isn't quite so clean. So I want to make it bad for myself. So I'm going to look something up. Give me a moment. No, it's not position. Those who are on Zoom can see what I'm doing at the moment. I'm just going to make one up on that. Sure, let's do that. No idea if it's going to work. I'm never I know it's going to happen, but I just want to give it a go. Okay, so the first thing I notice is when I do the derivative with respect to x and y, there's going to be x's and y's in both. It's not going to just cleanly turn out to be a single thing. You say? I'm going to do this, sorry. Just trying to, what, cool, that's that, that. The second notice is nearly a circle, so it's not quite a circle, because it's not just x squared, which is limits. So the first thing I want to tell you is how to figure out what number this line. I'm going to bring that 2 inside the square. And it'll be a root 2 inside the square. Because if I expand it, x squared on root 2 squared is x on 2, x squared on 2. The x squared is, if this had been an x squared plus y squared, that really would be a circle of radius 9. But I've replaced the x divided by something to stretch the x direction outwards by root 2. So this is a list of radius of root 2 in the x direction, and y in the y direction. Okay. I call the x radius, but I believe the official name is like the semi-major axis or something like that. It's close enough. And technically, y radius is 1. so again, if we have x on number squared plus y on number squared, those things with how y is in the x and y direction, which used to be in maths 1b pre-2018, but isn't anymore. And I'm not sure if lecturers realised after 5 years of curriculum change in maths 1b. Okay, so we're going to do the same thing. So let's call that square points. Find the points, and so f, I'll just mark here, f sub x. Now the y squared is constant multiplied by x, so it'll still be there, and the derivative of x squared is 2x. And the y is 2xy. Okay. And this is more complicated than the previous one, because the previous one, each of those derivatives only had one variable, and these both had 2. And I have to solve these simultaneously. Well, I'm going to start with number 2. Number 2, if x times y 0, then either x is 0 or y is 0. And I can start each of those back into the other one. Oh, crap, I'll stay with something worth it. I should have taken it. Let me change the question. Sorry. What's that over there? Oh, it's going to be okay. So the differentiation between x, I'll get y squared and 2x over 1. This is not what was going to be 0 is the only answer. No, it's equal to 1. So if x is 0, I'm going to start each of these, I'm going to start back to the other one. So if x equals 0, so number 1, and I'll get y squared plus 1 equals 0. So y squared is minus 1, which has no solutions. So again, yeah, okay. Can I make a x question again? Yeah, let's do it. I'm going to do the first one now. The point being is something like that, you just have there. And so y is also minus 1. So that is the x is 0 and y is 1, and the x is 0 and y is minus 1. That's what we've got so far. And that would be x is 0. So now I have to that. And if the y is equal to 0, I'll start back into 1. And I'll get y squared minus y 0 is 1. So I'll get 0 squared plus 2x minus 1 is 0. So 2x equals 1. So x equals a half. And so the x coordinate is a half and the y coordinate is 0. Cool. And now let's see if they're actually inside my region. 0, 1 is here, 0, minus 1 is here. Oh, they're on the boundary, so they're probably going to come up in the other one anyway. So I actually technically ignore those because they're on the boundary. I only know that one that's specifically inside. And 0, half 0 is here. So I only end up with 1 interior after all. Alright, cool. So maybe I should have made half of x, but I'm not going to change again. I'm here now. So if this is half of x, then these would have pulled in even further than they were. Now we have 3 of them. Now we have them all in. Now we have 4 that happens. Okay, and then now we have to do the boundary. For x equal 1. Thank you. And then I will have to set up my Lagrange multipliers. So h of x and y and lambda is my original function, which was xy squared plus x squared minus x minus lambda times this thing. And that has to be differentiated. I've already done y derivative of the x derivative of this, we did that earlier. That was y squared plus 2x minus 1. And now I have to do the x derivative of this. So the half will still be there, and derivative of 2x, x squared is 2x. Cool, hy. And that was 2xy. Lambda's not so it'll still be there, and I'll get this. And minus. Because that's the copy lambda. And all these have to be 0 simultaneously. And it is quite a bit more complicated than it was before, and it may be harder, and I may give up, but I will try my best to continue. So from number 1, I've got y squared plus 2x minus 1 minus x lambda equals x lambda. And from the other one, I've got 2xy equals 2y lambda. So maybe I should do what I did last time. I think it works. I multiply this one by 2y and by x. Damn it. Sorry. Not enough room. 1 times 2y. It should. Number 2 times x. And since they both equal the same thing, I think to each other. And yeah, it's not pretty. Everything for y, both y equals 0 is the answer. So that'd be good. Okay. Thank you. Y equals 0 is that solution. So if I divide by y, I'll get somewhere. Fingers crossed. So if y isn't 0, I get. I don't have my chances, people. I don't have chances. If I do by 2, it's about those. Oh, that's so cool. Oh, that's weird. Oh, I didn't expect to have it all. I'm so excited. If that's not that, you know, my chances are slim, but I was that cool. Oh, that's lovely. Oh, I love it. So y is x minus 1, or y is minus x minus 1. Huh. And that to something to the other one and see what happens. Alright. Alright, one more. So y equals 0. So number 3, which was this, which is this. So that gives me x squared on 2 plus 0 squared is 1. So x squared is 2. So x is also minus root 2. So I've got root 2 0 and minus root 2 0. Ah, they're these points, aren't they? They're these points here. Right on the sides there. That's cool. And y is x minus 1. So number 3. Even if I don't number 3, y is x minus 1. Because x minus 1 would be this line here. That would give me a point here and a point here. Plus left hand up 3 anyway. And so in 3, I've got x squared on 2 plus x minus 1 squared is 1. Because we've got an equation which has 2 solutions for x, whatever they are. Yep. 1 equals 0, that's cool. Oh, that wasn't too bad. That wasn't too bad at all. So x minus 3 on 2, x minus 2 equals 0. And so x equals 0, or 3 on 2, x minus 2 equals 0, which means x equals 4/3. Cool. And so we get, and therefore y equals 0 minus 1, which is minus 1, and y equals 4/3 minus 1, which is 1/3. So 4/3 is 1 and 1/3. So therefore I get 0 minus 1 and 4/3 is 1/3. Cool, isn't that not too bad, I have to say. What's that? I do want to see what 1 would do. Yeah. And so when I start this to so then 3, I've got x squared on 2 plus minus x minus 1 squared equals 1. That'll be the same thing, won't it? Different y's, yeah. And so that gets me to x equals 0, and x equals 4/3, and y would be minus 0 minus 1, which is 1, and y would be minus 4/3 minus 1, which would be minus 1/3. And so I get 0, 1, and 4/3 minus 1/3. Cool! And so just to go back to my diagram, actually, sorry again. So I reach down to half 0, and I have 0 minus 1, which is here, and 1, 0, 1, which is here, and 4/3, which is about here-ish. Oh, just a second. That's okay. 4 is less than root 2. And then 4 is back here. So I have those 5 points. And I have to sum them all in and see which of them is the least, which of them is the high, lowest, and I don't feel like doing that. I'm going to skip that bit. If you feel burning desire to figure out what the actual answer is, then you do it. I think they're all on the same side. If I was asked to just draw a diagram of where the points are that are in it, I wouldn't really figure out where I would draw the lines and mark them. Okay. I know that these ones that I've just got are all on boundary, so that's why I drew them on boundary. Cool. So I've figured out what F all those points were. Are they? Oh, you're right, these ones. Thank you. 9.20. Thank you. 7 points. equals number, etc. for 5 more. Yeah, I'm actually not figuring one. We'll give them the highest number that maximum is, and the lowest number that maximum is. And it's possible with minimum is, and it's possible that maximum have it more than one place in every state at those places. Yeah. But it's easy to get the same answer because it's a function. It's not likely to be the same answer with different x's in it, but it's possible maybe that's a y. Oh, okay. Oh, it is. Yeah, the answer will be the same, then y is the same. Then y is plus minus. So the answer at the same answer for both of these places, the same answer for both of these places. So each one of those is a maximum will have 2 results. So you'll be able to say the maximum is at this and this and is equal to this number. Yeah. Cool. Okay. Yep. It's the same as dimensions. It's just to make a boundary, you'll need there'll be more coordinates assigned to each other as you go. So a single constraint equal to a number will give you a surface, and you have the interior of that surface, like here, for example, and then you have to you end up with more things assigned to each other, unfortunately. But you end up with more equations at this point here as well. There's 3 dimensions of the x, y, z, and so you have 4 equations in 3 unknown. 4 equations. This equation is unknown. 4 equations going on. It should be possible to figure out what they are. Yeah. Cool. Okay. I'm going to that example. I have to say. It's important to know that something like that can happen. So I'm just going to warn you, maximum minimum at 2 places, at more than one place at the same time. And in that case, you say maximum occurs at, and then you say 2 points where the value is, and then the number of the value. So you make a statement like that. Cool. Right. And if I gave one of these exams, I can guarantee they would work very hard to write it in such a way that it wouldn't complicate to solve the equations that we've got. Yeah. Or they would not get any further way they set up the grand multiplier equations and say what the root is where and leave it at that. Right. That's the sort of thing that calculus lecturers will do. So get to this point to try and solve it. Something like that. While we're here, I do want to talk about the question. Let's last about Taylor's theorem and find local maximums of L, maximum minimum of what. So when you've got a multivariable function which is Rn to R, then when you do the first derivative, there's a different derivative for each x, right? Because so it's like f of x1, x2, xn equals number, right? And when you do the first derivative, there'll be df on dx1 and partial df on dx2 and partial df on dx3 and so on. And the first derivative is like the gradient of f, right? And that's got df on dx1 and df on dx2 and so on, like that. That's the gradient. And the second derivative is the hessian. It's not quite, it's like it's a second derivative. The electrical potential. Cool. And it's a matrix, and it has all the second derivatives in it. And so it'll start by having the second derivative with respect to x1, and the diagonal has second derivative with respect to x2, and so on and diagonal. And then this will be d squared f1, dx1, dx2. I can't remember what it doesn't matter. If the function is nice, the cross this will be a symmetric matrix, so it'll be okay. And so on, we'll fill them all out. So it'll be d on dx1 and d on dx2 and d on dx3 as like the headings that we're mentioning here, and d dx1 and d on dx2 as like headings here. And that's the Hessian matrix. And it has all the second derivatives, all the second half derivatives, of which there are n squared. So officially this one, we can see the functions of this one inside dx2 and then dx1, and so you find dx2. You could write this way instead, fx1, x1, and fx2, x1. And fill out all the rest of them, that works as well. The reason is the opposite way is because that's how it works. Closest thing to the f is the thing that happened first. So in this one, closest thing to the f is this one, and this one, the closest thing to the f is this one. So, not that that's the answer is the same. There's a theorem that says if your function is not stupid, then the answer is the same. But it's not stupid, it's like some sort of, there's continuity and stuff going on there. Okay, so the question is, I think that person, as opposed to being a question. Okay, you're now, after the day, I'm a stupid person, first one, I know what to say. So question, so the thing is that your Taylor's theorem goes that, so this old x here is this thing. Taylor's theorem goes that, I'll do that properly, just bear with me. This x naught. So Taylor's theorem is x naught plus a bit, and this thing you can imagine as just a point x. And so in my head, here we are in R2, and here's my x naught, and here's my h, and here is my x like that. So x naught plus h gets to the point x. And now you're going to calculate the value of the function at this new point x based on the value of the point x naught. And it will be f of x naught plus the gradient of f at x naught, because of vector, because of the... Sure they do. Why not? Yeah, whatever. Don't know that same gradient vector. Anyway. Under vector h. And so this point out, this is a row vector, and this is a column vector. So when you do row times column, you get a dot product, which is just a number. And then, yep. Not really using the column vector. In my head, gradient is a row vector. But anyway, you need to do whatever's in your lecturer's head. Apparently, gradient is a column vector. Sure. I'm sorry for leaving this straight, but thank you for bringing this all back. So we put down this is a gradient, so this is a gradient. Cool. And then we're going to have an instead with half of this. That. So this is a matrix. So we have a row, and a matrix, and a column. And the column and the matrix is a column. And so we have a row times column, so we get a number again. We should be getting the number, because that's the number answer this function. Plus some other stuff. And that other stuff is called the remainder number to x naught h. Yeah. That is Taylor's theorem for the second Taylor polynomial, right? This is the second degree Taylor polynomial for your function. So just to make it look more like, I just want to point something out. If you really want it to look more like a polynomial, you could write to x naught if you really want it. Obviously, that makes sense. If you really want it, because your Taylor's theorem in first year had x minus a, isn't it, right? When you do the polynomial. Well, the h is x minus a, and the a is x naught. So just wanted to point that out. They're the same thing. And presumably there's some sort of weird ass tensor thing after the third derivative, which is not right out. Because it's no, it is. And honestly, most physicists don't know the same derivative. So, and physicists invented most of our Multivariable Complex anyway. So, cool. Okay, so this thing, all the coordinates of h or x minus x naught get squared in this process. Okay, some of them will be, I just want to point something out here. When you model this out, you get h1 times all of these, because that's how multiplication works. And this h1 with the rows none of these, and so you're going to get an a times h1 squared, and a b times h1 h2, and a c times h1 h3, and a d times h2 h1, and a e times h2 squared, and f times h2 h3, and a g times h3 h1, and h. Oh crap! It's okay. We'll be fine. We can code. And I times h3 squared. And so what happens is that this here ends up being the coefficient of h1 squared, and so you can imagine that's headings of h1, h2, h3, and h1, h3, and so this one's up to h1, so h1 squared, this one's up to h1 squared, h2, and so that's what you end up with. And that's why it ends up being a quadratic equation. It all the h's get squared or multiplied by each other when you expand this thing out. That's what happens. So really it's a root 2 polynomial. Yeah. So here's the thing. That's correct, David. It's all essentially good if you like. But what do we do with this information? What we do with this information is if we happen to be a place where the first derivative is 0, that's not, if that's on x naught, and it's a critical point, then the derivative of x naught is 0, because that's what critical points are, places where the first derivative is 0. And so then, plus 0 comes up to 0 to this. And cool. So this is a critical point. We know it's probably a maximum or a minimum. And what we know is if we move just a little bit away from it, we'll get smaller and we place it as a maximum. Or we'll get bigger and we place it as a minimum. But if we can be sure that this quantity was positive, that would mean all the answers by answers that are bigger than this. And if we can be sure this number is negative, then that would mean that all the answers by this would be lower than this would be a maximum. So if we knew h transpose h, h transpose h was always positive, then f of x naught plus h is more than f of x naught. And it's a minimum. And if h transpose h is always negative, then f of x naught plus h would be less than f of x naught and would be a maximum. So I want to be, excuse my pun, it's not at all. I want to be definite about whether it's positive or negative. So I know it's a positive or negative definite matrix. That's the point of positive definiteness. You're definitely sure that it's positive if you do this at here. So hx naught positive definite means that h transpose hx or h is always positive, which means that it's a minimum. Yay. And hx naught negative definite means that h transpose hx naught h is always negative, which means it's a maximum. And if it's neither positive or negative, then you're not definite, so you don't know. Sorry, and be positive to do something when you calculate it down, but I don't remember which one it is. So I'm just going to do that. Oh, but I learned it specially. Alright. So this is okay, cool, that's second. So this means all the determinants are positive here. Is it positive in it? And it's a negative determinant here. No, positive. So that determinant, and that determinant, and that determinant, all are major determinants, which they call hi, are positive. And the other one else is negative. The first one being negative. So minus plus, etc. I know it's like writing with less than red, but that doesn't make sense to me. So you start with the first one being negative, and then positive, and then positive, and then positive. So if the second one's negative, then you can't either of these things, because of either of these patterns, and so it's some sort of ridiculous saddle point. Or not, I don't know. Then you 0, then we start to come on there too. Yeah. So in my head, it's all major determinants are all positive. So you have to do this first number, and then it'll do 2 in the corner, it'll do 3 in the corner, and so on until you get the whole matrix, and that all will be positive for it to be positive definite, which makes minimum, and that also makes minus first, and then plus minus. Yeah. Cool. So that's the original thing here. If we actually did that, just for an example, at this point, half 0, where that's y was, come on. Oh, got nothing mixed up. That's y squared plus x squared minus x, and we had point half 0, which was a critical point. We had fx was y squared plus 2x minus 1, and if y was 2xy, and then we did fxx, that gave me 2. That's nice. And then we did fxy, that gave me 2y. So differentiate with respect to y. And just to check if we did fyx, we differentiate with respect to x, and that also gives me 2y, and that usually should happen. And if yy would be 2x, and so my question matrix of xy is 2y, 2y, 2x, like that. And so at point half 0, it's 2, 0, 0, 1. And this is that determinant positive. And the determinant of the entire thing is 2, which is also positive, and so therefore it's positive, definite. And that's okay. The best criterion says that this is that h transpose h half 0 h is always positive, and so therefore is a minimum. A local minimum. Since it's the only one, it's probably the minimum too, but you know, I'm not going to guess on it. Yep. No, it has to start with minus. Yep. Yeah. And so this is a second derivative spot here, and it has to be negative if you in the direction, and so it can't be maximum unless there's a minus in this spot. Yeah. Otherwise, it's not clever in the x1 direction. Yeah. Cool. Yeah, it's probably going to be in the opposite order as well, but whatever. It has to be a minus. So these are actually both it's next to the next one, the next one. There are four things here. We need both to be negative. Otherwise, it's not going to be able to when I first learned this, I thought it was standard local negative, but you know the plus minus is the smallest one. Is that a question you asked? Cool, so I do start thinking this in, that's probably going to be a minimum, but it's not. Well, it's again, it can't be maximum, because it's definitely higher, lower than the maximum, so it's not maximum. Yeah. So that really interesting example, right? You're like, you should show that the 1.0 cannot be the maximum. Yeah, that's the minimum, can't be maximum. That'd be quite a big example question. I'm so glad I feel Alright, for that now, what is the next? I've got the try and do one thing, just to say once again. The main multiple breakdown in that word conversation, it's very good to write capitals and write all. Just something you need to know. Great. Okay. The most classic of all curves in multivariable calculus is the circle that is R. And it has the equation x squared plus y squared equals r squared. And it has parameterization. I use capital R not to confuse with this stupid verb equal anything. We have the classic equation of a circle, and it will have parameterization. R cos theta, R sin theta, cos theta between 0 and 2 pi. Would you like minus pi plus pi? Cool. That is the equation, and this is parameterization. That is the circle radius R. If you can find a circle in your 3D parameterization of the surface, everything will be easier. How do you feel about this parameterization? Cool. So I want to point something out. The unit circle, the R's out there, right? It has radius 1. And if you want to blow a circle up to the radius figure, all the points, I'm doing imagining here. This circle radius 1, and these are all the points on the circle. And if I imagine multiplying the points by R, then they all end up further out. So I multiply this entire set of coordinates by R, and the whole circle is further out than it was before. That is a way of imagining what's happened. I blow up cos theta sin theta. All coordinates by R. The reason I said that is so that I can describe how an ellipse happens. An ellipse happens. Let's radius A and y radius B, and that looks like this. Like that. It might be longer in this direction instead, which has to be the A. And it has an equation like this. Like that. What this does is that when you're in any equation, like that describes a curve or surface, if you replace x with x minus a, everything will be a times further away from the center. If you replace y with y by b, everything will be b times further away from the center. That's how it always works. So that's what the equation looks like. Because this time, if you divide the x coordinate a and also divide the y coordinate by b, that will shrink in with the little circle. That's what this is saying. So that's the equation. And that is the parameterization. Instead of multiplying both x and y by the same number, I multiply a by x coordinated by one number and the y coordinated by a different number. So multiplying this by a stretches it this way, and multiplying this by b stretches this way. The reason opposite is because this one is telling you every point b is exactly stretching it, and this one is shrinking in so that it matches the circle it came from. So affecting the inside of the equation as opposite of affecting the outside of the vector. How do you feel about this? Here's my unit circle. And that's one I'm doing. Here's my unit circle. And I would like to stretch it out this way by multiplying by a. So every point here, every vector, is going to be a times x. I'm going to do 2, if that's okay. So here's number 2. I'm going to make this point twice as far out this way. I'm going to make this point, its x coordinate is going to be twice as much as it was before. And this point, its x coordinate is twice as much as it was before. And this point, its x coordinate is twice as much as it was before. And this point, its x coordinate is twice as much as it was before. And so you end up with an order like that. So if you just multiply the x coordinate by the number of 2, then everything will be twice as wide this way as it was before, but it will be the same height as it was before. So just be even closer in. Here's theta, and this is cos theta into sin theta, right down the unit circle. If I multiply this distance here by 2, oh crap, that was that close. The surface here. If I multiply this distance here by 2 and keep this distance the same, then my triangle will be the same height as it was before, further out. And this is the new point on my ellipse. And every triangle does that, and so it gets stretched out like that. And then we do the same thing in the y direction and multiply y coordinate by y b, so it will stretch out upwards as well. That's my understanding of how it works. Every point has it. Yeah. So I'm just going to go to business. That's how I make a list of points. Here are all the points in circle here. So if I now multiply all of these points by 2, the x coordinate by 2 and y coordinate by 3. So x coordinate by 2 is going to be 0, y coordinate by 3 will be 0, 3. X coordinate by 2 will be 2, y coordinate by 3 will be 0. X coordinate by 2 will be 6 fifths, y coordinate by 3 will be 12 fifths. X coordinate by 2 will be 2 under 2. Y coordinate by 3 will be 3 on square root 2. X coordinate by 2 will be 1, y coordinate by 3 will be 3 root 3 on 2. Well, then 1 half 5 here. So this point here, I multiply, I stretch out this point here, and I stretch out this point, and I stretch out this point, and I stretch out this point, and so I'm tracing ellipse instead. Everyone has moved a little, has been stretched out in one direction differently than in the other direction. I'm just going to do one more thing. That's circle, equals theta, b sin theta, I'll use t instead of theta. If I make this a 2, it's stretched out that way. If I make this 3, it's stretched out this way. And that's how it produces it, by moving every point simultaneously, by multiplying all the x coordinates by 2, and multiplying all y coordinates by 3. And because I multiply the x and the y coordinates by different things, it's different in each two directions. That's why it is the way it is. Yeah. As you try to figure around it, we're going different speeds in different places now. Because that thing's going around a circle. Your object is going faster where the point is flatter than it is in its now. Okay. So if you want your circle to be centered at a different point, so the radius CT. I think vector-wise, And think about how to get to every point on that circle. So if I want to get to every point on the circle, first I'll get to point CD, and from there I'll go this journey, which is cosine sine theta. So it would be the point CD plus r cos theta r sine theta. This is the starting point, and this is the go from there to get to the point on the circle. And so you end up with C plus r cos theta d plus r sine theta. But if I take right like this, it's even okay to write like this. If you want. But you're allowed to use vectors at both points and journeys at any point, at any moment. And so I'm imagining that to get to these points, I start there, and then I go these journeys to get to those points. And if you want to ellipse to be a certain center, well, you do exactly the same thing. I will say what this does to the equation of the circle is. Sorry. It's this, by the way. So press C from the x to tell me how to get from here back to the original circle, S0, 0. And if you want an ellipse with x radius, A and y radius, B, center CD, then it would be same deal. You have the center CD, and then you would add on the A cos theta, B sine theta. Okay. Yeah. So there are your classic circles and ellipses, and there's one other parameterization you must know, which is the journey from one point to another on a straight line. Line segment from point A to point B. Yeah, this is why I have to get to every point on that line. And there are many ways to do it. But the quickest way is to get from A all the way to B. I start at the journey point B. Like from the very first time you learn vector, the journey point A to B. And that journey is, I'll get back on it. The journey from A to B is the vector AB, which is B minus A. That's how you calculate a vector from one point to another, the N minus B. Yep. And so if I want to do it that's partway between A and B, then I just have partway of A plus some model of B minus A. And you do T between 0 and 1. And Q is 0 and 3, you do 0 away from A. And Q is 0 and 3, you do 0 away from A. The T blocks into the journey of 1. So you say this is journey B. And if I want to go extend away, I'll go into that journey, and I don't get this relation. But that's the answer to the inversions. Which is the most classic parameterization of all. And so if one of those things where you expect when I scale something, you like expecting correct relation, it's much easier to do T 0 1 all of those things. So if you have this is like curve number 1, curve number 2, curve number 3, curve number 4 like that. Then we say curve number 1 goes from the point 1 minus 1 plus T times the journey from this point, which is 0, 2. And curve number 2 starts at the point 1, 1 and goes T times the journey from this point, which is minus 2, 0. And curve number 3 starts at the point 1 minus 1 and goes T times the journey from this point, which is 0, minus 2. And C4 starts at the point minus 1 minus 1 and goes T times the journey from this point, which is 2, 0. They are the four parameterizations of these equations of this way. And the T for all of them is going to be 0 to 1. Yeah. How are you feeling? Calculate this by doing that much act. Or just looking at it, I can see it's the vector 0, 2. Yeah. If you would prefer to parameterize it by arc length, then that's a whole thing. Such regions. No more. How much have to go? Have an example? Oh, yes, please do. Well, I'll finish this. These all T goes from 0 to 1. If you really want to parameterize it, you need to T go from 0 to 2 along this zone. And so I would, that's where, on this thing, you divide by the length, make a unit vector first, and then you multiply by how long the t is. But I don't see any particular reason why you want to parameterize it by arc length. It's okay to parameterize it by, but you're not going to figure out later when you do the integral. Because differentiating this will make the derivative will be twice as big as it was before, and so the length will be all worked out in the end. Yeah. Cool. So before we move on to a different question, how do you think about the parameterization of curves? Yep. Oh, I mean, if you had fun. So this entire thing is called C, and you had like integral around C of some function. Something like that. Is it ds at least? Then you have to do the integral separate on each of these things. And so you have to do the integral on C1 of f of x, y, ds. And in this case, the ds would be the derivative of this with respect to t times dt. So on C1, the position with respect to t is 1 minus 1 plus t 0, 2, and r dash t would be 0, 2. Multiply the ds, the derivative of the x coordinate you get 0, and the derivative of y coordinate you get 2. And so literally the coefficient t there. And so ds is r dash t dt. So as you move the t forward just a tiny bit, it causes the point along this curve to move just a tiny fraction of this vector 0, 2. That's the idea behind it. And so therefore the integral C1 of f of x, y, ds. You have to replace the x with 1 plus 0t and the y with minus 1 plus 2t. That's what it says. So you get just a second 0, 1, f of 1 minus 1 plus 2t. The dot in it. Okay. And so then you actually do the dot product, and that will give you a number involving t, and then you can do the integral as you expected. Why this thing? Okay. Okay. So you've got the option for what t is, and it goes from 1 to another, and it goes from 0 to 1. These is what t can be, all these numbers. And as you get to a particular point, a particular value of t, and you move forward past this point just a little bit. That's t. A little tiny change in t. And then you have a curve wherever the curve is. And the curve is the location of the point on the curve takes the value t. That's what our t means. And so as the t moves along here, this moves all the way along here. Pretty well. And it's going fast through some places numbers. So this point here maybe is related to this point here. So we sub t into this t into r, that point there, as an example. And then if the t moves forward a little bit, then this point will move forward a little bit as well. And so this will move forward just a little bit. Okay? And this, if you only, right, and this is technically this line is curved. Because it follows the curve of the thing. If I go this far, maybe it goes all around here. But remember the 3 distance, this doesn't feel straight. So this is the s here. That's this in here. So the tiny change along the curve itself, along the arc length of the curve, that's what the ds is. And so what derivatives tell you is how quickly a change on this side responds to a change on this side. That's true for all derivatives. And so ds is equal to something times dt. But this was a bit bigger, this also a bit bigger. And the something in this part has to be the derivative. And so it will be the derivative of the position you're at with respect to t, which is the r dash t. Yeah. That's my vague understanding of it. So r dash is how quickly r moves in the x and y coordinate each move and r and t moves. And if you move just a little tiny bit of the t, those x, y, and z coordinates will move in such a way you move along the curve. And it'll feel straight. And so that will cause you to have something that's tangent to the curve, and very close to the curve is the same thing along the curve. But the whole point of derivatives is that you're very close to it and feel straight. Alright? Okay. Very slowly, and then I'm going to stop. So you said set a region. I can give an example. The set of x's and y's presumably are 2, such that 1 is less than or equal to x squared minus y squared. Oh well. Okay, it's with a plus. That'd be good. Yeah, I'm not sure if this is make way. Okay. It is a hyperbola. Just so you know, math 1b in the past, we're all about hyperbolas. Just so you know, just FYI. X squared minus y squared equals 1. The fraction x equals plus y plus minus x, and it goes like this. I know it opens this way because when x is 0, there's no solution to y, so it doesn't make y itself. So you can't have negative y squared being w y squared minus 1. So it looks like this, that's a hyperbola. And this splits the page into 3 regions, and it's only equal to 1 in these regions, it has to be more than 1 on some regions, less than on others, and 0, 0, 0 squared minus 0 squared is less than 1, so these are places where it's less than 1, and these are places where it's more than 1. Yeah. And I'm especially using width and knowledge, probably. I don't know if it needs to make limit. Yeah. So the right way of saying what is going on here, and what is going on here, and how do they overlap, basically. Where are the edges of this? So this is 1, and x squared minus y squared equals 2. Well, that would be slightly different. And if we're really paying attention, I mean that this is the same method of expression, I would see that it's the y direction group 2. Because we're less than 2 stretches out, so it's actually that. Yep. And inside we go less than 2 and the outside goes 3. And so we have 2 of them. Wow. I'm hoping they're not that nasty to you. Well, no, 2. So the inside of this hyperbola is less than 2, and the outside of this hyperbola is more than 2, so it's this region here between. Yay. Ugh. So this was less than 1 is very nice, the outside of this one, and the inside of this one, and so it's the space between them. That's nasty. I don't think that is particularly nice. I feel for you. But if it wasn't that nasty, I'll tell you the one that I was, I'm going to have to do this one. Do that one. What is that? Well, x squared equals on this thing and a on the outside. And one is. Oh, that's great. I love it. Just say. I choose not to draw that diagram. I draw this diagram. So that's where x squared plus y squared equals 1. It's a little bit rather than it should be, but that's where x squared plus y squared equals 2. Yep. I don't want it where x squared plus y squared is. So I want x squared plus y to be more than 1. So I do not want it to be less than 1, and that's the less than 1. Not that bit. And I want x squared plus y to be less than 2. I don't want it to be less than 2, so not that bit. So the bit I really want to be in between them. Sometimes easier across it, you don't want. So this is where x squared plus y squared is greater than 2. And this is where x squared plus y squared is less than 1. And so the thing I really want is this bit here. So I could have done the same thing with my hyperbola as well. Of course, I don't want both of them. These are plain open. I'm colored in the middle that I do want. Oh, how do I know? I tested the point x, y, yes, exactly how I did it. So at the point 0, 0, 0 squared plus y is not more than 1, and so it's not less than 1. Because that circle is the dividing line between being more and less than 1. And so 1 point being less than 1, on the inside would mean less than 1 spot. Yeah. And that happens in these as well. Like you can actually just sub things in, and pick points that are, you know where it crosses over, and so the points in between the 1 point in each zone is the one that you want. That's how I did this as well. I put 0, 0 in here, that counts as less than 1. If I put any point out here, like 2, 0, that counts as more than 1, and so that gives you the answers that I want. Something to zero as a go. I'm not in next year, like all of you, but I'm trying to notice how this thing is done. It's one of the very things in all of your math courses that you will do, but you won't know what their thought processes are, and they won't know what their thought processes are until you ask them. So how did you decide that? And then push them when they ask. Yep, that's what I said aloud. Consider each equality, draw the curve corresponding to the edge, test the mean points, and voila, I keep these testing units. I'll do it. I didn't draw all the edges, but I draw all the edges of this. Go, well, this point has a flag that doesn't satisfy both of them simultaneously, no, it doesn't out. But this point here satisfies both of them simultaneously. Yes, that equals this entire using. Does this point satisfy both of them simultaneously? No, this entire using that. Yeah, that should be the correct thing. All right, well, thank you.